Okay, so I just kind of recap where we are, and I'll also mention a little bit about what we're going to do. Actually, first I think I'll mention about what we're going to do. So I mentioned, I think last week, so we've got essentially 3 pairs of lectures left, if you see what I mean. So remember that your homework is due in on Friday at my office as normal. So that's sheet 5, which is essentially about this topic of weighted majority algorithms and sequential investment. Okay, so hand that in on Friday. Then, in addition to that, I gave you all and emailed you all a copy of last year's exam paper. So that's due the following Friday. Okay, so not this Friday coming, but the one after, if you want it to be marked. Okay, it doesn't count towards your grade for the course, but maybe you want to try to go at it anyway, and then it's a chance for you to get some feedback on a kind of real exam. Okay, and obviously best preparation for this year's exam is last year's exam. Okay. So next week we'll go through the solutions in the tutorial to that, to the exercise sheet. In the last class we'll go through the solutions to last year's exam, okay? And then with the remaining 2 hours, I'll probably give like a kind of an overview of the course as a whole, sort of what we've done, you know, what are the main points, and also give a bit of a look ahead for what happens next. So if I had another 33 hours of lecture time or so, what would I cover? Okay, and that is actually useful for some of you because you know, if you're doing your thesis dissertation, it will probably, and it's with me, then it'll probably be on that topic. Okay, so if you're doing sort of 60 credits of your exam, might be sort of pointed by what we do in those 2 hours. Okay, so the kind of starting point for that. Okay, right, good. So that's what we'll do for the remaining kind of 6 hours of class time. Are there any questions about that?
How many of the problems will be accounted for the homework?
Oh yeah. So how many questions are there? 3 is.
4.
Is it 2? I think it was more than that. Let me look at it. Let's have a look. It'd probably be 2 out of. If it's 4, it'll be 2, and if it's 3, it'll be 2, and if it's 5, then might be 3, depending on how easy they are. Let me have a look. So here we go. Materials, exercises. Here's your exercises. That's exercise sheet 5, isn't it? So this one. No, that's not the right one. No, it's not the right one here either. Okay, I'll look it up for you. But if it's, we'll go with the formula that if it's 3 questions, then it's the best of the 2 marks that you get. If it's 4 questions, then it'll be the best of the 2 marks you get it. And if it's 5 questions, let's say it's the best 3. Okay. The first 2 questions on the Zuma-Hofting inequality, so they should be fairly straightforward, or at least it's kind of textbook stuff, so you can look that up. And of the remaining questions, they're more relevant to your kind of exam sort of setting. Okay. At least you want to remember. Okay, right. So now let's get on with what we covered last time. So we're looking at a kind of problem of sequential investment. Okay, so we spent some time looking at online learning algorithms. That's where you try to kind of estimate and predict relative to a set of experts what the best best algorithm you can come up with follows the behavior of those. Okay, and obviously that seems like quite a useful thing when you're considering investing in a market. You essentially have expert advice or a number of stocks which you're then tracking or following. Okay, and then your job is to try and get the best rate of return. Okay, now, so last time we looked at a special example of this, and this is a horse racing example. So the idea was that you turn up at a set of horse races, there's going to be T of these, and you can bet some money on the sets of horses that are racing each time. So there's N horses, okay? And only one of them is going to win, and that's the one you're going to make some multiple of your money on, okay? And you essentially need to distribute your wealth over the sets of horses, and then only one set amount of money carries through to the next period, okay? And then we introduce this idea of the regret of the policy compared to a set of policies. So you can imagine there are certain people giving you tips about which horses are going to win, and you look at how much money you made with your algorithm compared to how much money they made with their advice. Okay, so that gives you the regret of your policy compared to a set of experts given by this set script Q. Okay, we were particularly interested in this notion of minimax regret. Okay, so the regret is how much I literally regret the performance of my algorithm compared to the performance of the experts. Okay, so it looks at the relative behavior of those. Okay, now we're looking for something that's quite robust against that, and indeed sometimes this kind of minimax regret is known as robust or robust optimization. So the idea is, regardless of what happens in the horse races, okay, this is the worst thing that can happen. Okay, so looking kind of worst case scenario. Okay, and then we're looking for the policy that is best against the worst case scenario. So this is called minimax because there's the minimum and a maximum here. Okay, so this comes up quite a lot in different ideas of optimization. Essentially, you have an optimization problem where you're trying to get the best outcome possible, but some of the parameters are unknown. So you're looking for the best outcome for the best algorithm for the worst case scenario. Okay, and then we showed that in the case of horse racing, there is a way that you can summarize the expert advice that you've had so far into a policy called a normalized maximum likelihood forecaster. Okay, so here you aggregate together the behavior, the predictions of all the different experts that you had. Okay, take the maximum of those, and that is your weight that you apply to each outcome of the horse racing. Okay, and we could show that actually achieves the minimax regret. Okay, so there's a policy that is best for the worst case scenario. Okay, so that's sort of like really well hedged against really bad outcomes, essentially, in this market. Okay, so then we prove that. Now what we want to consider is, as we started to mention about last time, but I'll go over this again. Okay, so let's discuss again. Okay, so today we're going to develop the theory that we considered last time, but now we're going to consider it for investments. Okay, so previously we only had one winner and everyone else, all other money was lost. Okay, now we're going to have a set of stocks, okay, n of them, just like we had n horses in each race. Okay, and each unit of time their value is going to increase or decrease by some relative amount. Okay, so it's not just a 0 and a 1, but some stocks could double, some stocks could halve in value from one time period to the next. Okay, and we're going to invest over a period of time of t days. Okay, and our goal, again, is the same as before. It's the goal of maximizing our final wealth relative to the wealth of some reference strategies. Okay, so that could be like following the FTSE 100 or following, you've got a hedge fund that you're working with and they're giving you some stock advice or whatever. Okay, so it's how do you summarize the different pieces of advice that you're getting together, okay, and form an investment strategy. Okay, okay, so in this setting, rather than just having zeros and ones, we're going to have a market vector S. This is going to give the relative prices in the stocks over each given time period. Okay, so for each stock, S gives the amount. So let's say stock 1 doubles in price, then S1 would be equal to 2. Okay, and then a sequence of market vectors. Okay, so S of tau for tau equals 1 to t. Okay, we're going to summarize that with the notion script H. Okay, so H here really means history, the history up until time t. Okay, so that's going to denote the market set of market vectors before time t. Okay, so given the relative changes in the stocks in the market, we're going to consider an investment as a probability distribution that gives the proportions of wealth that you've invested in each asset or each stock. Okay, so here, and I remember there was a typo, so these Q's are supposed to be pi's. Okay, and pi I. Okay, So if I put a proportion pi I of my wealth in stock I, then that wealth is going to be multiplied by SI. Okay? And then if I sum that up, that's going to give me the total increase or decrease in my wealth. Okay? It's going to give me my wealth change, okay, from this time period to the next. Okay? And in an investment strategy, pi is a sequence of investments, okay, where at each time t, pi I, given the history up until that point, gives me the amount of money that I'm going to invest in stock I. Okay? Now, so then we defined the notion of the wealth factor of an investment strategy. Okay? So if I started with 1 unit of wealth at time 0, and I followed a policy pi, okay, at each time, okay, then this would give me the total amount of wealth that I would have at time capital T. Okay? So this is the amount of money I've made over capital T units of time, okay, from investing 1 unit of money. Right? And then we see that we can write certain policies within this framework. Okay? So one popular choice is the buy and hold policies, which are investment strategies where you distribute your initial wealth in some fixed proportion at the first time instance. Okay, so at time 0, you decide I'm going to divide my stocks and then maybe evenly divide my stocks, my wealth between these stocks. Okay, and then just see what happens. Okay, and I don't trade afterwards. So it's like this: you trade at time 0 and then you don't do any trading afterwards. Okay, that's a buy and hold strategy. And we see that we can write the wealth factor in this way, that QI is the initial amount of money that I put in asset I, and that's the increase in its price. Okay, and so that gives me the total wealth change that I get from that strategy. Okay, one we're going to consider a bit more is constantly rebalanced portfolios. Okay, so this is one where I keep a fixed proportion of my wealth, here F, invested in each asset. Okay? So here, I just decide I'm going to have an equal proportion of my money in each asset. Then I earn some money, okay? And then I just redistribute the wealth, so I've got an equal proportion of my wealth in each asset again. Okay? So that's more like sort of tracking the market or something like this. Okay? So these would be sort of a bunch of different market trackers, essentially. Okay? And again, we can get the wealth factor for that guy as well. Okay? Once again, we can consider the notion of the regret of these strategies and also the minimax regret. Okay? So here, the regret of a policy pi amongst some reference set of strategies, and I've used script I here, so that means that should be a script I, apologies, and that should be a script I. Okay, so with respect to set I, okay, and given the history that occurs, okay, the wealth factor, the regret, is the log of the best wealth factor, so that's the investment strategy in this set that made the most money, okay, compared to the amount of money that I made, okay? And then I take logarithms, okay? So I look at the relative increase in the wealth of the best investment strategy, and I compare it with mine. So you could think of it like this, that maybe the best investment strategy in here, okay, makes a rate of like 10% or something like this, okay? And the reason that I take logs is so I get 10%. I don't get like initial wealth of 100 times 110, or 1.1, okay? So we're taking logs, so we get the the sort of rate of increase here. Okay? So I'm looking at, they might get 10% and I might get 5%, and so my regret is 5%, for example. Okay? And so obviously you can see here that the smaller the regret is, the better my policy is doing. Okay? And the bigger my regret is, as in literally, the more I regret not following the advice of the best expert. Okay? All right. Again, we're going to consider a minimax framework. So it's like, what is the best policy for the worst case scenario? Okay? So here, W of T of I is going to be the minimum policy when I've maximized the regret over the sets of histories that can occur. Okay? So I look at the worst case regret and I say which policy is the best for that. Okay? And again, what we're going to find out is that we can construct a policy that achieves the minimax regret, specifically for constantly rebalanced portfolios, for these kind of market trackers. Okay, so you could have a bunch of market tracking portfolios, okay, and there's a policy that will get you the same rate of interest as the best one, asymptotically, essentially. Okay, so that's sort of the premise of what we're going for here. Okay, so I'm going to spend a little bit of time just interpreting what we mean by the minimax regret, and also we'll discuss, well, probably now I'll just discuss a little bit compared to the horse racing example. Okay, so the one thing to say is that essentially, because there's two things that make, well, there's essentially one thing that makes this a more difficult problem than the horse racing example. The horse racing example, the sorts of histories that can happen are much more limited. Okay, so it's like one winner, everyone else loses. Okay, so it's kind of simpler than like some people multiply their wealth by 10 and some people half it. It could be anything in between that. Okay, so the sets of things that can happen is more complicated. Okay, what we're going to prove though is in the case of constantly rebalanced portfolios, in fact, the two are the same. All right, they're both as difficult as one another. Okay, this is, and like I say, what this is essentially proving is that, so the first part in horse racing is really more related to the area of information theory, where you're trying to guess what the next bit is. Okay, you've got a sequence, a stream of zeros and ones, and you're trying to guess what the next 0, 1 vector is going to be. Okay, and in fact, I've seen people, write algorithms which are doing like online compression algorithms and things like this for trying to do predicting the prices of bitcoins and things like this, and they can work and get good Sharpe ratio out of that. So there is this link between sort of computer science information theory and stock investment, okay? Because they're both can be considered as sequential investment problems, or there are problems in both areas that can be considered as sequential learning problems. Okay, good. All right, that's about that. So now let's discuss a bit about the minimax wealth ratio here, okay? So the first thing to say is more or less what I said verbally, but let's just sort of write it out. So if we can show that the regret of some history is based on function f of t, okay, then you have the same growth rate as the best investment strategy in P, altered by some factor f of t. Okay? So, well, this is just follows really from the definition of the regret over here. So now let's start writing down the answers for this. Okay, so the regret T of pi, and I'll stick with the notation P, I don't know, yeah. Given a history, given that equals f of t, okay, if I look at the definition from over here, that's really saying that taking exponentials on both sides, so raising everything to the power of e to the x, I'm going to have the maximum over the wealth factors of all the policies that I've considered, divided by the wealth factor of my policy, okay, given the history, and then that's going to be, well, equal to f of t, okay? So then we just rearrange. Oh, I've forgotten an exponential on there, apologies. Okay. So, essentially, if we're getting like a kind of fixed rate of interest out of this, okay, so let's suppose that's sort of the optimal rate of interest over time t periods, okay, and let's suppose that we got really low regret. So remember we had this notion of Hannan consistency, meaning that f of t is little o of t, okay, then it's saying that essentially the rate of interest that I get out of my policy is the same as the rate of interest of the best policy there, okay? So getting low regret or Hannan consistent regret in this framework, okay, means that I'm getting the same rate of interest as the best investor in this class, okay? And again, like I say, within this setting, we're not considering a probabilistic framework. So when we're looking at these min-max type problems, we're saying if we can get low regret, we're saying we're robust against all market eventualities, essentially, okay? Okay. Right, so we'll keep interpreting a little bit more. So now we've got this slightly obtuse thing of the min-max regret over here, okay? So now given that exercise, we can interpret what it means for the min-max regret as well, okay? So, okay, so we're going to show here that if the min-max regret with respect to a set of investment strategies P is less than or equal to some function f of t, okay, then there exists a policy pi such that regardless of what happens in the history, in the past, okay, the wealth factor, my wealth factor is better than the best wealth factor within the set of policies. Okay? So I just say that again. If the wealth factor here is relatively small, the smaller it is, okay, the more this means that the wealth factor of there exists a policy, so that regardless of what happened in the history, I'm within that factor of the best. Okay? So I sometimes write it out this way when I'm teaching like game theory. So min-max theorems, like I mentioned, come out in game theory. It's sort of saying like, there exists a policy that I can follow that regardless of what the world chucks at me, I can still do good. Okay? So in game theory, if you've covered in the game theory before, it's the same sort of situation where we consider the notion of the value of a game. The idea is that regardless of what think of the world as being an adversary who's trying to give you the worst stock outcome possible, you can say, regardless of what happens with that, I can still get a good policy out. Okay? Provided I can get a nice low F of t here. All right? Okay. So let's prove why that's true. So, well, W T of P, the minimax regret, is what it says it is. It's the minimum over the sets of policies. Then the maximum over the sets of histories, okay, of the regret. Okay? Regret at time t with respect to these policies given the history. Okay? And I'm going to assume that's less than f of t. Okay? Actually, I might do this just to make things a little bit super rigorous. I'm going to make that strict inequality here. Okay? All right. So, if the minimum over pi is less than f of t, there must exist a policy where this term is less than f of t. Do you agree with that? Yeah? So that implies there exists a pi such that okay? And then, well, if the maximum over all the histories of this term is less than f of t, yeah, that means for every history that occurs, the regret has to be less than this quantity. Okay? Okay. And then I proved in the last exercise, so exercise 145, okay, that implies this. So this is the same as max pi over p wealth factor I over h of t is less than or equal to the wealth factor of pi of h of t e to the f of t. Okay? So the reason for this exercise is as a way of kind of interpreting what this means by minimax regret. It's saying there exists a policy that regardless of what happens, okay, I can be within a factor f of the optimal rate of return. Okay? Right. Okay. So now we're going to start to look at how we can kind of incorporate these ideas of the kind of horse racing market, where you have to guess a kind of 0-1 vector at each period of time, and look at how we can kind of apply that theory that we developed last time into this kind of sequential investment. Okay, so we're taking that step from gambling into investment. Okay. All right. So we'll need some definitions. So a market vector that has only one non-zero component is called a Kelly market vector. Okay, there's a guy called Kelly, invented these, so he's named after him. So it's just a 0-1 vector. Okay. Note that we consider exactly Kelly market vectors in the horse racing example. All right. So the special case where the histories were only Kelly market vectors was exactly the horse racing example. Okay. Okay, so now what we're going to try to do is we want to consider the differences with investment policies and prediction policies. Okay, so when I say an investment policy, I mean there's a market vector that's going to happen, and I have to spread my wealth over the different stocks, and then each unit of wealth is going to be multiplied by some amount. Okay, and when I consider a prediction policy, what I mean is I'm going to spread my wealth, or my predictions, over a number of horses, and only one of those predictions is going to be correct. Okay? Okay. So one of the things to say is that for every investment policy, we can define a prediction policy, and for every prediction policy, I can come up with an investment policy. Okay? Doesn't mean they're equivalent, but there's ways I can take something that's for prediction, make it for investment. There's a way I can take something for investment, make it do predictions with it. Okay? So that's what we're first going to talk about. Okay? Okay, so for every investment policy, we can define a prediction policy. In particular, if I take an investment policy pi, okay, so I'm going to be using pi's for investment policies, and I'm going to try as best as possible to use p's for prediction policies. Okay? So if I have investment policy pi, I can define a prediction policy, which is just the prediction my investment policy would have made on stock I, given a Kelly market vector as its history. Okay? So here I'm just taking the investment policy, proportion of wealth in I given a Kelly market vector history. Okay, so that's the kind of the easy one. You just say this is how much, given the history of stock prices, which are all zeros and ones, what have my investment strategy done, and we just do that for prediction. Okay, that's kind of easy. The next one is to kind of consider the prediction strategies. Now, prediction strategies, the input is just 0 and 1 vector, so I just get a bunch of horse races, okay? But I need to predict something where there's actually weights associated with the stock changes, so it's doubling and halving the stock. It's not one wins and one loses, okay? So I need to kind of place that into the kind of winning and losing framework into a investment framework where there's a kind of relative shift in the price. Okay? So in particular what we do, so for every prediction policy, I can define an investment policy or strategy. Okay? So given a prediction strategy P, as considered in the horse racing example, we can also define an investment strategy. Okay? In particular, the investment strategy here is going to say that given the history of the stock prices up until time t, but not including time t, the amount of money that I invest in stock I, and there's a small typo that should be an I rather than a J. Okay, so that should be I, not J, or that should be J, whichever you like. Okay, so what I'm going to do is essentially take an average. Okay, so the prediction strategy has a probability that it assigns to the history up until that point, and then given that history, it's got a prediction of what's going to happen at time t, which is given by this. Okay, and then I'm going to reweight it by the changes in the stocks according to that history. Okay, so if the stocks went up a lot, then obviously that prediction is going to be given more weight under this normalization, whereas if the stocks didn't go up very much, this gives a smaller weight. Okay, so essentially just kind of average over the predictions and then multiply up by the changes in the stocks. Okay. All right. And then, because this doesn't sum to 1, we're just going to divide by a normalizing constant, okay, which is going to be this. That's the thing that makes this sum to 1, okay? So it's just a way of kind of adjusting the weight to say that, you know, given what's happened in the past, if it's a good prediction, my judge of it being a good prediction is the weighted product of all the increases in the stocks as given by the predictions. Okay? Right. Okay. I mean, there could be other ways of taking a prediction strategy and making investment strategies. This is just one way of doing that. But it's going to be a useful one because what we're going to see is we can take our normalized maximum likelihood prediction strategy and apply it to investment problems. And this is going to be the correct definition where we can come up with an investment strategy that's going to be quite robust to different histories or stock price histories. Okay? Right. Okay, so one thing we can prove is that the wealth factor of an investment strategy induced by a prediction policy is actually exactly this normalizing constant over here. Okay? So that's kind of handy. Okay, so the thing that I divide my prediction strategy by to make it a probability distribution is exactly the wealth factor of that policy. Okay? So we can show why that's true. Okay? So that means we've got a kind of nice, reasonably nice closed form expression for what the wealth factor is. Okay? So let's go about proving that. Okay. So given our definition of a wealth factor, the wealth factor of a policy pi, given the history, is just the product of the changes in the stock prices at each time. Okay? I won't put a T there, that's transpose. I'll use a dash for transpose, okay? Okay. So let's just look at one of the terms in this wealth factor, okay? So it's just, there's a vector of stock prices, the market vector, dot producted with our investment strategy or investment policy, okay? So let's look at this. So let's look at one term. Okay, so we've got S of t, the market vector, dotted with the investment strategy. Okay. Now that's just the sum of all the stocks, okay, multiplied by the prediction given in the past. And now usually I've been putting like an I in here for the ith stock, okay, but let me write it slightly differently. Let me write h of t, where that's a 0, 1 vector, or if it's one I, then I make that an I there. Does that make sense? So rather than writing pi of 1 here, I'll write pi of 1, 0, 0, 0, 0 n times, and rather than writing, say, pi of 2 for the prediction for the second stock, I'll write pi of 0, 1, all the way up to 0. Okay, does that make sense? And just a little bit of a change of notation, but nothing major. And I'll do the same here. Okay. So I'm doing that over all h of t's. Okay. So now I'm going to chuck in the definition of pi of t h of t. Right? So I'm going to apply this definition up here. Right? And what you can see is I've got a sum over a bunch of 0, 1 vectors at time t, and a sum of a bunch of 0, 1 vectors up until time t minus 1. Okay, so let's just write that out. So the thing to pay attention to is that we've got two sums going on here. So we've got a sum of h of t, okay, then we've got s of t of h of t, okay, and then here I've got my pi of t, which is a sum of histories, okay, of 0, 1 vectors. Okay, and then times by this term here. Okay. Oh, and that should be a t minus 1 h of tau. Okay. And then I need to divide by 9 normalizing constant, which was f of t. Okay, so I've just substituted in there the definition of pi. Okay, so there to there is just the def of pi. Okay. Right. And then what we can notice is that I've got a sum of the history. Okay, so if I multiply this by this, I could think of this being like a bit like a Bayesian way of doing things. That I've got a conditional given the current, and that's the next thing that happens given that conditional. Okay. And also notice I've got one term left over from this product. I could think of this being like the next term in this product. Okay? So I could think of taking this s of t, h of t, and putting it into that product over there. Okay? And I can also think that actually I'm not summing over 0, 1 vectors up until, and I guess that should be t minus 1 here, up till t minus 1. But I'm actually doing it over vectors of histories up until t. So I could replace the double sum with the histories for up till t. Okay. You get the. So I can replace these two with that. Okay. Then I can take this s and I can absorb it into this product. Okay? And I can also absorb these two together. Okay? So let's see how that's going to go for us. So I've got a sum over h of t given h of t minus 1 times h of t. So that's going to give me p of capital H of t. All right. Just thinking I was doing things in a Bayesian way. Then I can think of this as the last term in that product. So rather than go to t minus 1, I go up to t now. And then I divide by f of t. Okay? Now notice that f of t is exactly this sum. So f of t is the sum of h of t, p of h of t times this product. So it's exactly that guy. Okay? So this guy at the top is just f of t plus 1. Okay, so that is exactly that. Okay. So then finally, what I'm doing is I'm producting, that's just one term in this product. Okay. But I've got, again, a bit like in the weighted majority algorithm, notice we've got one of these interpolating products again. Okay. So if I put this inside this product here, we're going to sort of cancel out diagonally the terms. Okay. So remember, like we had Wt plus 1 divided by Wt times Wt divided by Wt minus 1, and the terms would cancel out. Okay? So the wealth factor of the policy, given the set of histories, is equal to the product from t equals 1 to capital T. Okay, well, let's do with capital T's here. F of t plus 1 divided by f of t. But we know for these products, that's just going to give us only the last term. Okay, which is what we wanted. Okay? So it's interesting that actually for that set of policies, if we take a prediction policy and induce the investment policy, the normalizing constant is exactly the wealth factor for those cases. Okay, that's one of the reasons we've chosen this class of prediction policies. Okay, so there's a quick look ahead for after the break. So what we're going to do next is, now that we have a way of changing prediction policies into investment policies into prediction policies, what we're going to show is that for the class of constantly rebalanced portfolios, the minimax regret, or the minimax wealth factor for investment is exactly the same as that for prediction. So that's essentially showing that prediction and investment are of equal difficulty when we're considering these kind of constantly rebalanced market tracking portfolios. Okay? So, and given we had a prediction strategy that worked well for that, that means we've also got an investment strategy that we can work with. Okay? Right, so we'll have a 10-minute break now, and then we'll have a go at that after the break, proving this theorem.